Hello and welcome to this session. In this session, we're going to talk about the least squares approximation. Least squares is a method of fitting what we call a line of best fit to a set of discrete data of a given interval. The best approximation in the least square sense is defined as that for which the constant ci for I, 1, 2, 3, up to n, so I is a natural number in this case, are determined so that the aggregate of e squared of a given interval is a minimum. Now here e is the deviation of the actual point from the line of best fit. So that if we are given some set of data with n data points, and this being a discrete data with the coordinates x1, y1, x2, y2, x3, y3, all the way up to xn, yn, the least squares line will take the form y is a function of x, and the deviation of the individual point from the line will basically be the value of y at a given point minus the value of the function f of x evaluated at that point. So in this case, we can think of some points. So we have a point here which we can call x1, y1, and another point here which we can call, say, x2, y2, and another point, say we have a point there which we can call x3, y3. I'll only use those 3 points for clarity. Then suppose that if I believe that the line here is a straight line, then I can draw a line that I think best represents this data. Now, the difference between the value of y at a given point, such as the point x is equals to x2 here. Say at this point, at the point x2 here, some point here, which is x2, we can get the corresponding value of y, which is the value at this point here. But we can also get the value of the function at that point. So moving from x2 all the way up to the point in the line, then we can get the value of the function at the point x is equals to x2. Now the difference between these two values is what we are calling the e, the deviation of the line, or rather the deviation of the point from this line. Now for the line of best fit in the least square sense, then the sum of the square deviations must be a minimum. So we can write the sum of the square deviation for I is 1 to n is a minimum. So that if we set p to be the sum of this deviation, then the problem is to minimize p. So we state our problem as minimize p, which is equals to the sum of ei squared, I taking the values from 1 all the way up to n. And ei is the difference between the actual value of y at this point minus the value of y, or rather the value of the function f of x evaluated at that point. So if we want to fit a linear line, if our line of best fit is a straight line, then we replace f of x, or we substitute f of x is equals to a plus bxi. And so we need to find the values of the constants a and b such that we minimize p. So notice that in our case here, because we had written ei in this form, then when we replace f of xi with this function, we shall write ei is equals to yi minus a minus b xi. Then we can now square this quantity here and substitute here, so that we can write p as the sum from I is 1 to n. Then we have yi minus a minus b xi squared. So we need to minimize. This is the quantity that we must minimize. This is the quantity that we must minimize. So how do we minimize a function? To minimize a function, we need to differentiate the function with respect to the variable quantity and then equate the result to 0. Since the line is determined, a straight line is determined by the values of a and b, then we see that p is a function of a and b. So we need to differentiate p with respect to the variables a and b. In this case, we find the first order partial derivatives of p with respect to the variable quantities, that is a and b. We then equate the derivative to 0 and solve the resulting equations. Once we do that, we get a set of two equations that we call the normal equations. We call these two the normal equations. So to determine the values of a and b, given a set of data, we need to find the sum of y values, we need to find the sum of x values, the sum of x times y, the sum of xi values, and the sum of xi squared. Then n is the number of data points. So as we said, we call these two the normal equations. And these two equations can be expressed in matrix form. See that the unknown quantities here are a and b. So we can even write this matrix, this system as a z is equals to c, where a is the coefficient matrix here, and c is this vector. Then z will be the vector AB containing the unknown quantities a and b. So once we write that, then we can solve that equation using the matrix method. Now we are going to use a MATLAB to solve this, given a set of data. So you are given a set of data, the values of x and the corresponding values of y. So we have x1, x2, x3, x4, and so on, and the corresponding values of y, y1, y2, y3, y4, and so on. We may have more points. So in this case, see that in order to carry out the squares approximation, we will require to know the value of n. N is the number of points. Then we need to add the values of x. So in this case, when you are given a set of data x and y, and you are given x1 and the corresponding value of y, x2 and the corresponding value of y, y2, x3 and the corresponding value of y, and so on, assuming that we have 4 points, then we need the value of the x values here, we need the value of the y values here, which we are calling yi. Then see that we need another column here where we can multiply x times y, and then we have x squared. So that here we have x1 times y1, x2 times y2, x3 times y3, and so on, x4 times y4, and then we square the x values. So we have x1 squared, x2 squared, x3 squared, and so on, x4 squared. Then we get the sum for this column, xi times yi, and the sum for this column, xi squared. So once we have all these totals, then we can count the number of pairs here. How many data points we have? We have 1, 2, 3, 4. So in this case, n will be equals to 4 for this particular example, because we have 4 pairs or 4 points, n being the number of pairs. So we can then substitute these values in our matrix here to get the matrix A. Then Z will be the vector AB. Then we can determine the sum of y, the sum of xi, yi, to give us the vector B, or we can call it C. Then the next thing is to enter data into a MATLAB program. The first thing is the input data, the values of xi and yi. We can enter the values. The input function here will read the values from the keyboard. So this one prompts the user to enter the values of x. The next line will prompt the user to enter the values of y. Notice that we can enter the values directly without these input functions. The next, we need to know the size of data, the number of pairs. We can use the n to be the length of x, the number of values, the number of elements in the vector x. So we can use the length of x. Then we can compute the sums, the sum of x. The sum you compute using the sum function. So you can write sum of xi, that will compute the sum. This will compute x1 plus x2 plus x3 plus x4, the sum of the x values. Then the sum of x squared. So you write sum of x I, then dot, then the power you use the hat and write 2. This will compute the sum of x1 squared plus x2 squared plus x3 squared, and so on. As many points as we have, each of those elements will be squared. Then the vector B, or we can call it C, I will call it C. So we write the sum of y, so in this case we shall write the sum of yi. Then the next one will be the sum of xi dot times is the asterisk yi. So notice that we use the dot product here because we want to multiply the corresponding elements of x to the element of y. The elements occupying the same relative position in these two vectors, that's what we want to multiply, and then we add them. And then the next thing is to, so we have, these are the sums. And the next thing is to compute the inverse. The inverse you can use, if you have a matrix A and you want to compute the inverse, you can use the inverse operator. So you write the inverse of A like that to compute the inverse. But we shall see that there is an easier way of computing this, which works much faster when you are solving a problem. so that we can write, because the solution is expressed as A inverse times B, that's the matrix method. There are two ways of doing it. You write the inverse of A times B, or you can write, normally MATLAB will accept the division. If you write this, then you are dividing A by B. But if you write this, you are dividing B by A. Because now our expression here, although we don't like this, is like we are saying 1 over A. If these were numbers, we would write 1 over A times B, although we cannot write this in matrix. But if these were numbers, we would write this, which we would then write as B divided by A. Then matrix may accept something like this by using B divided by A. Here you are dividing B by A. So MATLAB will accept that even with matrices, although normally we cannot write this if A and B are matrices. But MATLAB will accept the division of this kind. So this one works much faster in MATLAB than this. So we are going to use the division. And then we can construct the line. So I'm going to go to MATLAB and we see this line by line. So the first one, I have a set of data, the points xi, the values 1, 4, 9, 12, 14, and 17. These are 6 entries. And the corresponding values of y, the 6 values here as well. We can use commas or spaces. Let me use comma for easier feasibility. So minus 3.97, 5.18, 20.43, 29.58, that 5.68, and 44.83. These are 6 entries. N is the length of xi. So it will just count how many elements do we have here, and then that will be the n. So there will be 6 in this case. Then now A, remember how we wrote our matrix A. It was maybe we can go back to that and see the first law. If you look at where we had A, the coefficient matrix, the first row we have n and the sum of x, and the second row we have the sum of x and the sum of x squared. So when we go back to our MATLAB session, then we can write the first law n and the sum of xi, then put a semicolon, meaning that that is the end of the first law. Then the second law we have the sum of xi and the sum of xi squared. Then C, what we had written as B, but I'll write C here. We have the sum of yi and the sum of, that is the first, if you look at C, where we had C, where we had the matrix B here, the first row, this is a column vector. The first element is yi, the sum of yi. The second element is the sum of xi times yi. So we show that we write that in MATLAB. And we have the sum of yi. We put a semicolon. indicating that that was the error of the first law. Then the second law, we have the sum of xi times yi. Now here, I'll call this one z, as we had it there. So the z is the solution to that, A inverse times C. So the first element is A, and the second element is B. Then we output the results using the fprintf function. So y is equals to A plus bx. So you see y is equals to, then I have a placeholder, which is the percent sign here is the placeholder. Then 0.5, that will be indicating that the solution should be correct to 5 decimal places. F, indicating that I want to output a float. Then plus, then another placeholder, 0.5, again 5 decimal places. F is a float. Then times x. This one is an x character. Then we have the values of A and B. So when I run this, I get the function y, the equation of a straight line. Y is equals to minus 7.02 plus 3.05 x, which is an equation of a straight line. I can change the data here. If you look at the case here, n, if I type n here in the command window and press enter, I'll see that n is 6. Meaning that there were 6 entries here. But I can check this data. I have the values like 4, 6, 8, 12. Now I have 19. So now I have only 4. Let me put 13 there. I have only 4 entries. So I'll put some corresponding values here. Say 8, 12, 17, 25. For values again. When I run this one, when I run this with the now the given data, if I type n in the command window, I will expect to see a value of 4. N is 4. Because we have 4 entries here. The equation of the line is y is equals to 0.86592 plus 1.88827x. This is the equation of the line of best fit to this given data. If I shade this data, or if I add some few points, maybe I add some 3 other points, say we have 15, 20, 25, or 27, and I add the corresponding values here. Say 36, 45, and 57, for example. Now I have 7 points. I learn this one again. I'll get the line. This one is a different line because this one is a different set of data. If I type n in the command window, I'll say now I have 7 points. I now have 7 points. I can count here 1, 2, 3, 4, 5, 6, 7. So n is basically the length of xi, which is the number of elements of the variable x. And I have the equation of the line of best fit here. So basically this is how you can use MATLAB to obtain the line of best fit using the least squares method. So I think I'll stop at that point for now. In the next video, I'll talk about the Newton-Gregory method.